I might confuse you. And that is the purpose, because I am totally confused by what I have recently found. Totally, I'm mystified. And that's why, oh, there should be an exclamation mark or a question mark after light. I really don't know what the meaning is of what I've discovered, but by chance. But it is so simple, I'm absolutely amazed. And I just want to present it to you for whatever that is worth. So it's well known that complex scalar fields rigorously describe free classical electromagnetic fields. This was done way back by Green, H.S. Green, and Wolf. So those of you who are interested in knowing how, we can talk about it later, but let's accept that as a fact. So you have a complex scalar field which obeys the standard wave equation, which is Lorentz invariant. Now, consider a stationary solution of this form, where this is complex, and the only time dependence comes there. Strangely, if you take such a psi and operate with the first time derivative on it, you get this equation. Now, when I first saw it, I was just going to take the second time derivative, which will give you the Helmholtz equation, but I just stopped because I couldn't believe what I saw. It is the Schrödinger equation. It has the same operator structure as the Schrödinger equation. There is a single time derivative with a factor of I, and there is this factor. There is, of course, no invariant mass here. So it's not a non-relativistic Schrödinger equation. In fact, I'll show you later, you can multiply it by h bar and put it into an exactly Schrödinger type of equation, but the mass factor which will come is not an invariant mass. It's precisely half of h bar omega by c square, effective mass of a photon. You may say, I don't know. I'm simply telling you that I am stunned by what I see. Okay, the next step is, there always exists a Hermitian displacement operator. And so you have this non-commutation also. I'm not saying they have this, by the way, I'm not interpreting them, and I'm not claiming they're exactly the same as quantum mechanics. No, I'm simply pointing out what I see. And of course, if I go back and take a second derivative of time derivative of this, another I omega will come here. And of course, as is very well known, you will get this Helmholtz equation. And that's all I have to say, actually. That's practically the end of my talk. But let me carry on a little more. So this equation is well known to describe stationary classical light. However, let me do a bit of trick. I have been working on Bohmian mechanics for a long time, and I love this idea of writing the psi function as a real part and an imaginary part, because that actually often gives you insights which you otherwise don't have. So I'll use this where rho and phi are both real, and then plug it into that equation, Schrödinger-like equation, and separate the real and imaginary parts. And from the imaginary part, you will get this equation where Q is defined as this. Those of you who know the quantum potential will immediately see the quantum potential there without, of course, the h bar. And you get a continuity equation. The explicit time-dependent part, I have put equal to 0 because this the amplitude is assumed to be not time-dependent. The entire time dependence has been taken out. So that is 0, but that's a minor point. So this term, which I write as a curly Q, is strikingly similar to the quantum potential and couples the phase and the amplitude of the wave. Because without this Q term, these two equations are decoupled. But with the Q, they are coupled. That is, rho and phi are not independent. In quantum mechanics, we know that this happens, and that is why the amplitude and the phase are coupled, and that's why you see interference patterns. Now, in classical mechanics, as opposed to classical optics, I would like to emphasize this point. When people talk about classical physics, they don't distinguish between classical mechanics and classical optics. There's a huge difference, in my opinion. In classical optics, you have interference. Nowadays, we know we have entanglement, we have Bell violations, all sorts of things may not have exactly the same physical interpretation as in quantum mechanics. But all these things are now well established. And here also what happens is, in this Q term actually couples the amplitude and the phase, and that's how you see interference in classical optics. So nothing quantum mechanical about anything. But then if I write phi, and this is the point where I'm, I think I have a legitimate claim to write phi like that. But where I want S to be the action, so I need some unit of action, which I have written as h bar. You can take it as anything you like. Doesn't matter. Eventually, you have to fix it by comparing your results with experiments, and you will get h bar. So I've anticipated it should be h bar and written it like that, but there's no theoretical compulsion at all to do that. Then this equation becomes this equation, where h is now written like this because it's time and space have been separated. You can, as in classical mechanics, we can always write S as some W, which is independent of time, times the entire time dependence comes here, where E is a conserved energy. And this equation then becomes like this. And now, of course, this is no longer h bar independent. You get this h bar here, and this then becomes the actual quantum potential. Now, one can define the gradient of W as the momentum, as usually you do. If I use that as h bar k, then my Hamiltonian becomes this.
Could you explain what was the m star in the previous slide? M star?
M star. Oh, sorry. Yeah. M star is this value. This is just a notational thing. It's the same thing as this. I made it to look as if there is a mass. There is no mass. But dimensionally, it's mass. And then you have this as your continuity equation, very similar to what Professor Weismann was talking about this morning, Bohmian. But it has nothing to do with Bohm, nothing to do with quantum theory. It's just the energy flow lines. So it's connected with the Poynting vector, if you want. Now, this rho is of the mod psi square. If we interpret this, actually we have to use a normalization condition. But if you do that, then this can be, no, here I don't need to do that. This is, in fact, is the time-independent field intensity at a point. So remember that if the wave function is of the form 2, that is, I do not split it into a real and imaginary part. I write a complex part times just the exponential of minus I omega t, then I don't get all these features. But the moment I write it as a real part times imaginary part, that's the polar form, I somehow get things which look very similar to quantum mechanics. I'm puzzled. What is happening? This is my genuine question. I'm puzzled. Have we discovered, are these equations, the standard equations which you use, the wave equation and the Helmholtz equation, do they unify the quantum theory and the classical theory, or what is happening? I'm not very sure. This is an honest and genuine question to all of you. Okay, let me carry forward a bit to recapitulate, therefore. We started with this equation for a complex psi. When you take the first derivative, you get a Schrödinger-like structure. When you get a second derivative, you get back the Helmholtz equation. But this is, of course, all true only for stationary states, not in general. The first and the third equations are familiar classical equations. But as we have seen, the second equation, which is derived from the first and which leads to the second, has a Schrödinger-like structure. And with a polar form of the wave function, it gives rise to quantum-like results. To the best of my knowledge, this has not been noticed before. This is the best of my knowledge. It shows that a quantum-like structure lies hidden in classical massless scalar field theory. Now, those of you who want a little more technical details, let me just say, and this is from the paper by Green and Wolf. One can write. You see, if we want to write an action for a scalar field with a mass term, then this field has the mechanical dimension of like this, and S is guaranteed to have the mechanical dimension of action, standard. But if the mass is 0, then one has to introduce an independent unit of action so that one has an effective mass like this. In principle, the unit of action is an arbitrary constant which is fixed by comparison with empirical data. Now, the correspondence with classical electrodynamics is given like this. You write this is a complex thing, this is your Lagrangian. And so this corresponds, so this can be mapped to this as the Lagrangian, where these are the vector potentials. And the Hamiltonian density is given by this, which corresponds to this. And the momentum density corresponds to this. But it is written like this. And if you put P equal to h bar times the displacement operator, you actually get the well-known commutation relations. However, this does not necessarily have any implication of disturbance or measurements, which still remain classical and unproblematic. The fact that the formulation of a Hamilton-Jacobi theory of a massless classical field requires the introduction of a fundamental unit of action in order even to define the action S leads to a natural definition of an effective mass of the field. And this equation, as I had said before, that equation you get by taking the first time derivative only can be written in this form, where m star is defined by h bar omega over 2c square, which is exactly of the Schrödinger form, but completely relativistic. And now let me come to that point. Why am I claiming that it is completely relativistic? Because people have pointed out that the moment you write distinguish between space and time, you've already spoiled Lorentz invariance. Okay? So, but there is a trick which I'm very fond of, which I learned when I was doing my, in my days of being a particle physicist or field theorist, and I was very much worried about the classical works by Tomonaga and Schwinger and so on. And in fact, Dipankar and I used the Tomonaga-Schwinger equation once to put the EPR state in a manifestly covariant form. So I remembered that, read it up again, and let me just tell you what that is. So a remark concerning the restriction to stationary solutions. So it might appear that the separation into space and time is non-relativistic. This can be avoided by foliating the Minkowski manifold by space-like hypersurfaces sigma, whose normal at every point is time-like. That is, any 2 points of that surface has a space-like separation. Hence, each point on a particular sigma has its own time, so that there is no preferred time frame that defines absolute simultaneity. In fact, you have infinitely many times. The Lorentz transformations will transform the surfaces from sigma to some sigma primed with local times t p primed, where p primed will be on the sigma primed, and one is free to choose any one of these foliations. Thus, space-time separation can be done fully relativistically. A scalar field can be defined as a functional over a particular space-like surface, and time evolution will take you from one such space-like surface to another, and so on. And the Schrödinger equation can actually be written in this form, where this is a functional derivative which you take by deforming the surface sigma locally and then taking the limit of that volume going to 0. All this was done in those old 1940s by Tomonaga and independently by Schwinger. I didn't understand Schwinger's paper well, but I understood it when I read Dyson's paper, which puts everything together very nicely. And there you will see this equation coming. So actually, there's nothing non-relativistic, and people who do optics, they know very well that when they use the Helmholtz equation and they use stationary state solutions, they are not breaking Lorentz invariance because they are still doing optics. So thank you very much. I hope I have confused you sufficiently and provoked you sufficiently.
Switched off the mic perhaps. Okay, maybe I can speak loudly. Thank you, and thanks for lots of questions, I'm sure.
Lots.
Thanks for that. Yeah, so you did succeed in confusing me. Because
Sorry?
You did succeed in confusing me because I don't know if you remember on one of my slides this morning, I had something very similar, but it was just transverse. But I defined the mass as h bar omega over c squared.
Right.
But you have h bar omega over 2c squared.
Yeah,
yes.
That comes somehow.
So, right.
It's just the structure of the equation. If you want to write it in the Schrödinger form, you have to stick in a 2m. That's all. There's nothing mysterious. It's just a definition. But strangely, if you want to identify it as an effective mass, there is this factor 2. I'm making a guess now. This is scalar field theory. Electrodynamics is not. So there are 2 states of helicity. Maybe this factor will go away when you take the 2 states of helicity. My guess. In fact, when I saw your slide, I was a bit heartened. I was really apprehensive in giving this talk, let me tell you. I'm so puzzled. I don't know, is it a unified theory or what is happening? By the way, the paper was thrown out by the editorial board without sending it to any referee. They didn't consider it. It is so absurd, they just rejected it. Then I spoke to Dipankar and I said, should I talk about it? He said, yes, please do talk about it. So he encouraged me, and here I am. But I saw a smile on my friend's face, which has encouraged me that I don't think I've made any mistake. I've just exposed the structure to you.
Sir, in your slides, you expressed the theory of light in terms of a complex scalar field.
Yeah.
And normally we study using a vector field, which is a gauge field. Now, complex scalar field has a U1 invariance and has a conserved charge.
No, here there's no charge because the mass is 0. This is ordinary electrodynamics where you often use electric and magnetic fields, E and B, and E stars and B stars, but then finally you take the real part.
Okay.
If you look at Born and Wolf's book or this paper by Green and Wolf, they will explain in detail, but this is very technical point, so I don't want to.
Thank you for a sufficiently confusing talk. I just want to make a suggestion. You know, there is a 1949 paper of Dirac called the
Multi-time, many time.
No, that is with Podolsky and somebody. Dirac, Fock, and Podolsky. That's 1930s. Many-time formalism.
Many time.
I'm talking of the 1949 paper,
okay.
Forms of Relativistic Dynamics. Forms of Relativistic Dynamics, that was for Einstein's 70th birthday. And he shows that any special relativistic set of equations can be written in several forms. And there's one form called the front form. Front form. That is something that Simon, Sudarshan, and I have exploited for the Maxwell equations. And the curious thing, but it's completely, it can be worked out, within the Poincaré group, there is a subgroup which has the structure of the Galilei group in 2 space dimensions. And if you carry through the work analysis properly, you will find in the front form, things look like non-relativistic Schrodinger type equations. But there is no H bar. This is purely at the classical level.
So you had seen these much earlier, yeah.
So
okay.
there is
I was not aware.
There's no need in that traditional approach to introduce something like H bar for dimensional reasons. There's no need. The only thing is you made a 2-step procedure. Second order equation, intermediate first order equation, and then again second. That first order structure comes out in the front form, but with some approximations.
With
some approximations. But
no, I mean in the approximation of stationary states, yeah.
No. We have well, you have to use what are called the front form variables.
Oh, that thing.
Instead of t, x, y, z, you use x, y, t plus z, and t minus z, and express Maxwell's equations in those variables. Then it starts looking like non-relativistic 2-dimensional quantum mechanics, but no H bar. So we might like to compare it
here, and there is no compulsion to introduce. I just thought that if I wanted to do a Hamilton-Jacobi theory with action, then there's no other way. And somehow or other, then quantum-looking results come out.
Question?
Alex?
So just if you take the problem the other way around, you write Maxwell's equations as a Schrodinger equation using the Riemann-Silberstein 3 vectors. So you have a Schrodinger equation, and of course it's not a
complex
scalar.
combinations.
Right.
Yeah.
And then of course you have this H bar that appeared. So I think Peter Holland wrote a paper about 10 years ago on the connection between this approach and Bohmian mechanics. So it could be maybe useful in this context. That was the comment.
I'm aware of that, but then one has to use those Silberstein.
That's it's a
forms.
vectorial Schrodinger equation, of course. It's not scalar.
Yeah, you're right. He has that alternative formulation, and Green and Wolf use the simple scalar structure.
A naive question. To make sense of many of these, equations for Maxwell and for Schrodinger equations, physical sense, one of the things that's very important is to understand the boundary conditions and
what conditions?
The boundary conditions.
Boundary conditions.
And the surfaces on which one can impose them.
That's a very important point.
Does that cause any difficulties in this interpretation of yours?
I wouldn't be able to answer the question now, but this idea of the boundary conditions came to me because I said I get 2 sorts of solutions from the same equation basically. One quantum looking, the other classical, and one is familiar with the fact that partial differential equations solutions do depend on the boundary conditions. So what sort of boundary conditions are we thinking of when we see what we call classical light and when we see what we call quantum light. Now, very vaguely, I think that the state preparation is very important. At time t equals 0, what is the state you have produced in the lab? If you have produced a classical state, it should be described by the usual way. But if you use spontaneous down conversion and all that and produce genuine photon states, then you should use the other solution. Maybe this is the situation, I'm not sure, but it's something that occurred to me as a way of distinguishing these two kinds of solutions. But it's an incomplete answer.
We've thought about it.
Yes.
See, related to the issue of introduction of H bar, I have a small query. See, in the analogy between classical electrodynamics and the Schrodinger equation, people have noted that the finite wavelength of light can play a similar role in classical optics as the H bar plays in quantum mechanics. I mean, in classical mechanics, classical optics, you could have impreciseness in joint measurements because of the finite wavelength of light. And this is at the heart of the so-called classical entanglement. You can actually formulate your classical optics in terms of a first-order Schrodinger-like equation, and then you can have the usual Schmidt decomposition and entanglement.
No, it's not necessary.
It's one way of doing it. So
one way of doing it.
So my question is, instead of introducing H bar, if you were to, I mean, not bring in HR by hand, but use the fact that the wavelength of light is finite, and maybe, I mean, with proper dimensions, use that here.
Maybe, I don't know. As I said, that H bar can be anything. It has to be some fundamental constant having the dimension of action. That's all I require. But if I want to compare with experiment, I'm sure it will turn out to be H bar. But this thing, I am not very sure because the wavelength is a length, whereas for action, you need something more. So I don't know how to construct an action constant from a wavelength.
Okay, thanks. If there are no more questions, let's thank the speaker.